Gang, I want to draw your attention to this figure. We've seen this before, right? We've got a submerged vertical plate, a flat plate. Remember, we call that a lamina. And we want to calculate the fluid force on that flat submerged lamina, okay, which we've done before. So I've taken the liberty of somewhere between C and D, I've located some Y, and there's the corresponding differential rectangle that corresponds to it. You'll notice that I labeled the ends of the rectangle like we always do, right? And I've indicated that the depth of the rectangle is capital D minus Y, assuming that the surface of the fluid is located at capital D, okay? So I'm using an XY coordinate system. So I've got it written here in words. The differential element of fluid force is equal to the weight density of the fluid, right? That's these constants right here, times the depth of the rectangle times the area of the rectangle. So of course we could write like this, huh? And if I rearrange the factors, I can also write like this. Now remember from our work with centers of mass, this expression right here, do you remember what that is? Yeah, that's the differential element of mass. So I could actually write this way as well. Okay. So in any case, the total fluid force on that vertically submerged surface then is going to equal the sum of the fluid force on all those differential elements. Now, according to the figure, they're all going to range from C to D, and they're all going to have the same form, namely this expression right here. Okay. Now I'm going to algebraically manipulate this expression for a few steps, gang. First, I am going to distribute the G and the differential of M through this expression. How's that look? Okay, then I'll split that up into two integrals. Okay. Next, I think I'm going to factor out the G constant. Maybe take out the D from this as well. Yeah, I'll do that too. Okay, how's that look? Then what I'll do is, again, it's all algebra now, gang, no calculus, all algebra. I'm going to factor out the G from both terms, and I'm also going to factor out an integral, this integral. And that's going to leave me with capital D in the first term right here, minus, no G here because I factored it out, but the integral that's left, look at what that's going to leave, gang, when I factor this integral out. Okay, see that? Now, hopefully you recognize this expression, that formula right there. Okay, do you know what that is? Do you remember what that is? Yeah, that's actually that formula right there gives you the y coordinate of the center of mass. Yep. Now let me just make a quick aside, gang. It is customary, typically in physics and engineering, mainly engineering, I think, when you have a lamina of constant density, and that's all that we consider right now, okay, laminas of constant density, we typically say that they are homogeneous, okay? And the center of mass is often referred to in those cases as the centroid, okay, the centroid. So this would be the y-coordinate of the center of mass, otherwise known as the y-coordinate of the centroid, okay? So again, I'm going to rewrite my expression here. The differential element of mass, remember, that's rho dA. Okay, and I replaced that stuff in the red circle right there with the y-coordinate for the centroid or center of mass. Since rho is a constant, I can move that through the integral symbol. Okay, and in words, gang, in words, what this tells us is, I'm going to write it in a different color. Okay, the fluid force, okay, the fluid force on a vertically submerged plate, okay, of constant density, so a lamina, okay, is equal, excuse me, is equal to, in words, that's the weight density of the fluid, okay, so the weight density of the fluid, this expression right here, that's the depth of the centroid, and the third factor, the one in the middle, that's the area of the lamina. Okay, so the fluid force on a vertically submerged surface is equal to the weight density of the fluid times the depth of the centroid times the area of the lamina itself. Now that's particularly helpful for those of you that are going to go on to study engineering and fluid mechanics, I think it's called, okay? And this formula is especially useful because if you know already what the centroid of a surface is going to be, you don't have to actually calculate integrals, okay, the way that we did when we calculated fluid force. You know, what are the kind of things, what kind of shapes do you automatically know what the centroid is going to be? Well, circles for one, dead center, right? Squares and rectangles, dead center, you know, that kind of a thing. So if you already know what the center of mass is or the centroid of a surface is, then calculating fluid force can be done without the use of an integral.